In competitive exams like the NET, GATE, or IIT JAM, you are fighting two enemies simultaneously: the complexity of the problems and the clock. Under that pressure, it is tempting to rely on brute force memorization. Students often try to cram massive tables of combinatorial formulas, like the exact number of binary relations possible on a set, directly into their short-term memory. This creates flashcards covered in dense, abstract exponents. You are staring at 2 to the n squared minus n for one logical condition, and 3 to the n times n minus 1 over 2 for another, hoping they stay distinct. But stress jumbles these abstract terms. A minus sign flips, an n becomes a 2, and a single misplaced character in an exponent invalidates the entire calculation. To guarantee accuracy, we must learn to derive these formulas from first principles exactly when we need them. These student marginal notes show us how. They described a structural model used to reconstruct the math at will. Mathematical maturity comes from possessing these models, not from storing raw data. Let's build that model. At its baseline, a binary relation on a set is simply a collection of ordered pairs taken from that set. Visualizing these pairs as a loose, floating cluster is difficult to track. We need to impose a rigid geometric order. The perfect tool for this is an n by n matrix. We map every element of our set to both the rows and the columns. This creates a grid governed by binary logic. We place a 1 in a cell if that specific pair exists in our relation, and a 0 if it does not. Every possible binary relation on this set has a corresponding unique layout of 1s and 0s on this exact board. By shifting our perspective away from abstract set notation and onto a concrete matrix, we turn a complex combinatorial problem into a matter of simple geometry. Start with a blank canvas, a purely unconstrained relation on a set containing n elements. No rules, any pair is allowed. To find the total number of variations, we calculate the total area of our matrix. An n by n grid gives us exactly n squared total cells. Because there are no constraints on this general relation, every single one of those cells operates in a vacuum. Each cell has two choices, 0 or 1, and we make that choice n squared times. This results in 2 to the power of n squared total possible relations. This is our absolute ceiling. Every specific relation we study from here on is simply this same grid, with certain choices locked away by rules. Let's look at how rules change the grid, starting with reflexive relations. In a reflexive relation, every single element in the set must relate to itself. Element A1 must pair with A1, element A2 with A2, and so on. We can see the student working through this logic in the margin, marking out those specific self-pairs. On our grid, those self-pairs form a specific geometric feature, the main diagonal. The rule of reflexivity removes our choice here. These diagonal cells are forced to be 1. Since the matrix is n by n, there are exactly n cells on this diagonal. One choice per cell means 1 to the power of n, or just 1. Now look at the remaining space on the board. We take our total area of n squared and subtract the n diagonal cells. That leaves an off-diagonal area of n squared minus n. Reflexivity places no restrictions on these cells, so they retain their two independent binary choices. Multiply our one choice for the diagonal by the two choices for the rest of the board, and we derive 2 to the power of n squared minus n. The formula is a direct reflection of the grid's geography. Now let's tackle a harder challenge that frequently causes panic on exams: the asymmetric relation. The rule of asymmetry states that if element A points to B, B cannot point back to A. Additionally, self-loops are forbidden. Look at how the student breaks down this complex logic into a visual choice table. First, the no self-loops rule. We go to the main diagonal and lock all n cells to 0, one choice. Now we address the rest of the cells, but we have to shift our thinking. Because A pointing to B affects whether B can point to A, we can no longer treat cells independently. We must evaluate them as mirrored pairs across the diagonal. The rule binds them together. To find how many pairs we have, we take our off-diagonal area, n squared minus n, and divide it by 2. That gives us n times n minus 1 over 2 distinct pairs. Now look at the student's logic for a single pair. For any mirrored pair, option 1 is assigning a 1 to the first cell and a 0 to its mirror. Option 2 is the reverse, 0 and 1. Option 3 is setting both to 0. But setting both to 1 is an illegal state, as it violates asymmetry. We are left with exactly 3 legal states per pair. Because we have n times n minus 1 over 2 geographic pairs, and each pair has exactly 3 legal states, the total asymmetric relations is 3 to the power of n times n minus 1 over 2. What looks like a terrifying formula is just a spatial reality of the grid. By mapping abstract rules onto physical space, we tame them. We can now see the final formulas sitting next to the geometric footprints that create them. This geometric understanding is more robust than a memorized flashcard. If a formula slips during an exam, you don't need to panic. The matrix acts as a failsafe to quickly sketch the rules and reconstruct the derivation in seconds. At this level, mathematics rewards those who recognize deep structural patterns. Challenge yourself to apply this matrix logic to symmetric or irreflexive relations. By mapping these abstract mathematical theories onto rigid physical structures, it completely changes the way you solve them in real time. Stop trying to memorize everything. Draw the grid, map the rules, and the formula becomes a direct consequence of the geometry.